Rarely is a sample homogeneous, yet traditional electrochemical experiments measure an average response over the entire electrode-electrolyte interface. Analysis of an average response does not provide information on localized electrochemical reactions, leading to misinterpretation of data. This need to investigate localized phenomena has led to the emergence of scanning probe electrochemistry. The VersaSCAN from Princeton Applied Research allows you to elevate your research to another dimension. The VersaSCAN is a single research platform capable of providing spatial resolution to both electrochemical and materials-based measurements. Integration of a high-resolution, long-travel positioning system with multiple auxiliary components such as measurement probes, laser heads, and superior measurement instrumentation make the VersaSCAN the most versatile scanning system available. The Scanning Electrochemical Microscope, or SECM, integrates a positioning system, a bipotentiostat, and an ultra-microelectrode tip, allowing the user to enhance all applications of electrochemical research through chemical imaging. One such application, the study of porous membranes, has advanced fuel cell research through the analysis of proton exchange membranes, while the high-throughput screening of electrocatalysts by SECM has been employed to find a replacement for platinum as an oxygen reduction catalyst. The positioning system moves the tip close to the surface of the sample. The bipotentiostat polarizes both the sample and the tip independently and measures both resulting currents. In contrast to other surface imaging techniques, such as atomic force microscopy or Raman spectroscopy, SECM is far more affordable, allows for the study of larger samples with minimal impact, and provides for a modular laboratory research system. Applications of an SECM are as varied as the applications of electrochemistry itself. Key fields that have already benefited from SECM are biological sensors, electrochemical reaction kinetics, microfabrication, and corrosion mechanisms. The Scanning Vibrating Electrode Technique, or SVET, uses a single wire to measure potential gradients in solution. Measuring this gradient images the current at the sample surface, allowing the correlation of electrochemical intensity with visual inspection of a corrosion site or pit formation. Combined with Amatec's lock-in amplifier, the VersaSCAN provides the ultimate spatial resolution of corrosion pits at the micro level. A key application of SVET is the study of corrosion processes of bare metals. These include galvanic couples, welds, and local non-uniform corrosion events such as pits or crevices. Time-lapse experiments provide the capability to monitor corrosion events in real time, mimicking real-world environments. Additionally, there are many applications and references for the use of SVET for the detection of physiological electric currents associated with cell migration and synaptic communication in biological systems. Localized Electrochemical Impedance Spectroscopy, LEIS, employs the Princeton Applied Research VersaStat 3F to apply an AC voltage to the sample immersed in electrolyte. The global voltage causes AC current to flow at the electrode-electrolyte surface. This AC current varies spatially, allowing the determination of local impedances. This technique is particularly valuable in the evaluation of coatings and inhibitor efficacy in corrosion studies, as well as failure analysis of energy storage materials. There are two LEIS test methods for the researcher to choose from. The first method entails the charting of the local response of a sample as a function of applied AC frequency. The second allows the user to create a data map to characterize an AC response as a function of probe position at a set frequency. LEIS provides a spatially resolved impedance measurement that adds value to the research of inorganic and organic coatings, localized corrosion, coating integrity, variations in coating thickness, surface contamination, and inhibitor studies. The VersaSCAN Scanning Droplet Cell, or SDC, is a traditional 3-electrode experiment with a localized electrochemical cell scanned across the surface of a sample. Since electrochemistry occurs at an electrode-electrolyte interface, only the portion of the sample that is in contact with the droplet is being measured. This allows experiments to study a small area of a large sample. SDC experiments can be configured in one of two ways. First, the user can apply a constant bias, such as potential or current, and increment the position of the droplet, creating a data map. Second, the user can apply a static or dynamic electrochemical signal to perform experiments such as EIS, Tafel or cyclic voltammetry, as the droplet is held in a fixed location. Because the droplet is a self-contained 3-electrode chemical cell, the technique applies to all applications of electrochemistry. The VersaSCAN Kelvin probe technique is a non-destructive method to determine the relative work-function difference between the probe and the sample. This work function can be correlated to the corrosion or open circuit potential of bare or coated metals. One example of the application of the scanning Kelvin probe is the study of the surface of a material beneath a coating to detect active corrosion sites or identify the potential for future corrosion site development. The technique has additionally been applied to the field of forensics, solar cell research, and the development of organic light-emitting diodes. Based on the principle of a capacitor, SKP allows the user to set and maintain the probe-to-sample distance, enabling the researcher to negate topographical contributions across real-world surfaces. One example of this utility is the study of a pipe weld, in which the curvature of the pipe makes such analysis impossible with traditional techniques. In addition to being a non-destructive technique, SKP also allows for electrochemical analysis in the absence of electrolyte, preserving the sample for future analysis. The VersaSCAN Non-Contacting Optical Surface Profile, or OSP, is an option which generates relative height information that can be used as the basis for constant distance mode operation for all VersaSCAN techniques. The OSP technique can also be used to map topographic changes on a sample surface to characterize corrosion pit size, depth, and number. In addition, OSP provides highly accurate optical feedback with which the user can level the sample, reducing probe-to-sample distance variability. For more information about our VersaSCAN, including the many other auxiliary features, please visit www.princetonappliedresearch.com.